for 15 minutes. Thanks very much. Welcome once again to this course on Bayesian modeling, inference, prediction, and decision making. This is week 9 out of 10 weeks. There are a few new things on the web page. Perhaps I can orient you to those things first. We do not yet have the videos from week 8, but I'm guessing they'll come along pretty soon, so that has not been updated. But there's new material under week 9 that we'll be talking about today. Also, I posted the extra notes, the handwritten notes from up here at the document camera from last week. I'm going to be showing you Bayesian model averaging over the uncertainty in the subset of predictor variables in a much more interesting regression data set than the one we looked at last time. It's a data set in which the goal was to try to predict the daily maximum ozone concentration in the air in Los Angeles as a function of a number of meteorological predictors. And this data set was first analyzed by Leo Breiman and Jerry Friedman in a paper they published in JASA back in 1985. Leo was a faculty member at Berkeley in the late 70s and early 80s when I finished my PhD there, and I actually got to know a much more elaborate version of this data set because he taught a course on data analysis that I took, and the final project involved quite an elaborate analysis of data of this kind across multiple measurement locations in the LA basin over long periods of time with many, many predictor variables. So this data set here is a somewhat cut down version of that data set. I'll say more about that in a little while. My former PhD student at University of Bath, Dimitris Fouskakis, and his Greek colleague, Yannis Nsoufras, and I have been working on variable selection ourselves, and we also look at the ozone data. So I have given you the draft paper. This paper has been submitted to a journal but is not yet published, and it has an appendix in which we talk more about the data set. So I'll talk a bit about that today. We've been focusing mainly on inference and prediction so far, and I wanted to show you a practical example of Bayesian decision theory. This also arises from other work that I did with Dimitris, and so we'll be looking at lecture note 7, which is about the problem of trying to choose in regression settings from amongst a large number of predictor variables, but in a way that's more real-world practical, namely that most of the time when you are gathering data, or at least until fairly recently this was true, the x's, the predictor variables in regression, were not free. They came with a cost of data collection, and this will still be very much true for those of you who are in, for instance, the clinical trials business or analyzing clinical trials data. I know there are some people involved in drug company work and other medical work here in the class. From the very first moment as an undergraduate, when I began hearing about regression, it seemed odd to me that the goal was always expressed as the following, namely trying to find a subset of the predictor variables that did the best job in prediction. For example, prediction out of sample to avoid overfitting. And the reason I thought that was funny was that most of the time for data sets that are not of the kind that we are gathering in the Valley these days, where data is actually pretty cheap to acquire, but in many examples, the x's will differ from each other not only in how well they can predict the outcome y, but in how much they cost to collect. And so the problem of choosing a subset of x's becomes not a benefit-only problem in which we're trying to find that subset of x's that predicts the best out of sample, but a cost-benefit trade-off in which we look around for that subset of the x's that predicts as well as it can given how much the variables cost to collect. And what you'll end up finding when you create that trade-off is that you get very different sets of predictor variables when the costs vary considerably. And in fact, some variables that predict very well are left entirely out of the models because they cost too much relative to how much information they have in them. In our problem, we were trying to understand how to construct a scale that measured sickness at admission for hospital patients with pneumonia. And there was one particular variable that was a very strong predictor, but it was extraordinarily costly because it was formed by gathering many small elements all across the medical record and combining them in a particular way to create a scale. And it turned out that a subset of those elements carried most of the weight and was much cheaper. And so if you disaggregate the scale and focus only on its elements, then instead of having to pay for the entire scale, you can just pay for the parts of it that really help you. So we'll look at that a little bit today. We were able to solve that problem with Bayesian decision theory. What you want to do, of course, is to construct a utility function that trades off predictive accuracy on the one hand against data collection cost on the other hand. And so I'll show you how we did that. And in fact, we have a series of papers on this. We published a paper in JAS Applications in which the utility story unfolds with more detail than you're going to see in lecture note 7. I'm going to talk later today about how the Bayesian information criterion works, and we were able to develop a cost-adjusted version of it, BIC for short, and we published that work in the Annals of Applied Statistics. And then I think I've mentioned before that whenever you have a bivariate optimization problem, in this case we want two things at once that conflict with each other. We want high predictive accuracy and we also want low cost of data collection. There are really only two ways you can proceed. Method number one, you can work with a weight times one of the ingredients plus another weight times the other one. That brings it down from 2 dimensions down to 1, and then you can optimize in that 1 dimension, which is what the utility story does. And also it turns out what the cost-adjusted BIC does. Or the other way to go is to optimize on one of the variables subject to a constraint on the other. And that may well give rise to quite different answers, but it is a second and different way to reduce the dimension of the optimization problem down from 2 to 1. And so we wrote a paper about that also. It's natural in our context to try to maximize predictive accuracy subject to a bound on cost. And so we wrote a paper about that that appeared in the Journal of the Royal Statistical Society, Series C, the applied statistics part. I'm going to show you some results from the principal package at CRAN that does Bayesian nonparametric work. It's called DP package, and I've put the documentation for it from the CRAN repository on our webpage as well. And there's a bunch more of new code down here in the part with the code, in which I have firstly added a new example based on that ozone data for looking at Bayesian model averaging and also the BMS package. And then we have a whole bunch more code to look at for how to do Bayesian nonparametric modeling. So I think I'll start by catching up on those things because they represent extensions of what we did last week. And then I'm going to go back to our main methodology file that we haven't finished yet, namely the lecture notes part 5, in which we examine many different ways to compare one model with another. We haven't finished talking about those ideas, and I'll show you how to make them operational with code that actually lets you do it. So maybe first we'll start today by looking at, by re-examining the question of how to do variable selection in regression and in a way that propagates your uncertainty across models. Rather than choosing a single best model, you want to try to find the best 10 or the best 100 models and consider combining them in a model averaging fashion using that Bayesian model averaging technique we talked about before. So here's the data set for it. Doesn't look that nice to look at because it all got crammed together, and you'll see there's some NAs, there's some missing values that we're going to have to cope with as well. And then we have code that does the actual Bayesian model averaging. So let me go ahead and download this code to the desktop. And also download the data to the desktop. See if they manage to show up someplace where I could find them. So that's the code that we're going to go through, and here's the data set. In fact, I think I'll run the code here and read the data from a directory where the data set has been stored. Let's do that instead. So find where I put that. Okay, so this code assumes that you have put the data set into the directory where you're going to run the code, and it's called ozone-data.txt, and that's the name it has when you download it from the course website. So I'll get into R and change directory to the place where that data is. And begin telling you a bit about the data set itself. We have data on where there's one row for each day in the year 1976. And that was a leap year, so we have 366 rows. And we have initially only 9 predictor variables and 1 outcome. The outcome variable is the maximum ozone level on that particular day at a particular location in the Los Angeles basin. I don't know whether any of you have ever lived in Los Angeles. In particular, if you ever lived there back in the mid-1970s, but LA had a furious air control problem in the mid-70s, which is quite a bit better now. I spent some time there at the Rand Corporation. I've mentioned that to you before, from I think it was 1984 to 1991, and the air quality was already slowly improving, but was still quite bad. They used to have regular occurrences of what were called first stage smog alerts, meaning that the forecast was that the ozone and other pollutant levels would exceed the federal government's standard for clean air. And then warnings would be issued to people for doing things like curtailing how much vigorous outdoor activity they did. We always think of doing something like jogging as having always a net benefit for our health, apart from falling down and breaking your ankle or something like that. But in fact, when the air is really bad, you can actually end up with a net deficit in your health by trying to exercise vigorously in highly polluted air. And so the LA newspapers and the LA government would issue warnings about how bad the air was, and you would adjust your activities accordingly. And if it got to a second stage smog alert, then actual factories were ordered to shut down, ones that were making special pollutants. They used to have requirements where people with certain license plate endings on their license plates couldn't drive on particular days for really, really bad days to try to cut down on the ozone and so on. So that's our outcome variable. And it has a very long right-hand tail, as you might imagine. And so it's natural to think of transforming it to get close to normality, and the log transform turns out to work pretty well. Then we have a bunch of meteorological variables. The temperature at a nearby Air Force base, Sandberg, the atmospheric air pressure at 500 meters above the ground, I think it was, the relative humidity, the height of the inversion layer, if there was any inversion layer, because that traps smog underneath it, the wind speed, the strength of the air pressure gradient, the inversion layer, temperature difference between the top and the bottom of the inversion layer, and how many kilometers of visibility you had at that Air Force base. And these things were all measured at either, I'm forgetting now, at one point during the day, or else they were also based upon hourly averages, and perhaps a maximum was taken. We standardized all of these variables by subtracting off their mean and dividing by their standard deviation. We also standardized the outcome variable. That makes the regression easier to fit, because there will be, we're about to build things like interaction terms and quadratics and cubics, and they become less strongly correlated with each other if you standardize them first before you begin squaring and cubing them and so on. Also, there was a strong temporal effect, and so we had variables like month and day of week and actual date And all of that was irrelevant except to construct a variable called day of year, which was a simple linear index from 1 to 366. And naturally, you could imagine that would have some sort of sinusoidal behavior where things get worse in the summer and better in the winter, for example. So we start with 9 predictor variables and 1 outcome. And then we did exploratory data analyses using the routine that's available inside R for looking at non-parametric regression called LOS. In those days, the main one that one could have used was called LOWESS, but they have a better version now called LOESS. LOWESS stood for locally weighted scatterplot smooth, and was developed by a guy at Bell Labs called Bill Cleveland. And we found nonlinear relationships all the way up to the cubic level between the outcome and some variables, and lots of quadratic relationships. And so if you're going to try to approximate a complicated regression surface and do it in a parametric fashion, one simple thing you could try would be to build up the complication with linear terms and quadratic terms and cubic terms as necessary, and interaction terms, because they create another sort of complexity that can be helpful. So with 9 main effects, or linear terms, they are 9 times 8 over 2, which is equal to, what is that, I guess, 36, is that right? Two-way interaction terms, all formed by multiplying one variable against another after standardizing. And then our final model, it turned out, had 9 main effects and 9 quadratic terms, 2 cubic terms, and 36 two-way interactions. And so this is how, without much trouble at all, you get up from only 9 predictor variables up to 56 predictor variables by trying to create a rather complicated nonlinear surface. So that's the data set. And I'm going to bring it in. And there's a whole narrative in the Bayesian story about how to deal most appropriately from a scientific point of view with missing data. I don't know if you guys have thought carefully about that problem before, but the issue is actually tricky because you need to know something about why the data is missing to know how to deal with it. If the data values are what's called completely missing at random, then a reasonable thing to do that will reduce your amount of data that you have, but is a quick and fast thing to do, is something that people have been doing for decades now, namely simply delete all the rows in the data set that have 1 or more missing values and work only with the complete data. That will give you a loss of accuracy to some extent, especially if lots of rows are deleted in that fashion, but it will not introduce bias into the answers based upon the pattern of the missingness. Unfortunately, that state of affairs is not always true, and there are other reasons for data to be missing at random. You might have a variable in which that variable is missing more often when the outcome variable is large than when it's small. And so that would mean that the very missingness of that variable is itself informative. And it would be a bad idea simply to delete all the rows in the data set where that variable is missing, because you end up distorting the actual relationship. So the Bayesian story for handling missing data is particularly easy for me to describe to you, because missing data values are things that we don't know. The same way parameters in models are things we don't know. And so what do we do as Bayesians about missing data values? They have prior distributions, and we infer them along with the parameters of the model. And you can do something that's like a Gibbs sampler, that ham and eggs sort of story I told before. We temporarily pretend we know what the missing data is by filling it in by sampling from its posterior predictive distribution. And then with a complete data set, we learn about the parameters. Then we pretend we know the parameters, and we use them to predict the missing data values, and we iterate like that. And so although it's a complicated thing to do carefully, and entire books have been written about it that I could draw your attention to, there's a method that Don Rubin invented called multiple imputation that is an approximation to the full Bayes analysis for missing data. And these days, I don't think we need to approximate because we can actually do the thing right. But I'm not going to show you any examples of that during this course. That's an item that we'll just want to put on our list of things that are definitely worth your attention that didn't get covered in this course. And since we're coming to the end next week, I fear that list is going to have to start growing because there will be various things we won't get to cover. But I'm going to make a note to myself that I want to mention on the final day the Bayesian narrative for missing data and give you some references, for example. Okay, so let me read in the data, and I'll do that simple deletion of any row that has a missing object, one or more missing predictor values in it. And that turns out to reduce our sample size from 366 days down to 330 days. So we lost about 10% of the data. Not too bad. So I think I already changed directory. So let's just try reading it in. Okay, good. Now I'll put the outcome variable in a vector called y, which is the first column of the ozone data set. And I'll put all of the other columns, namely the ozone data set with column 1 omitted, I'll put that into a predictor matrix called X. And if we were simply going to do maximum likelihood regression with Gaussian errors, which corresponds to least squares regression, we can do that easily in the world of R with the linear model command, in which I say Y is modeled in terms of the tilde. Doesn't exactly stand for is distributed as the way it does in WinBugs or the way we write it on paper, but it essentially means y is thought to be a linear function of all the columns in X is what that expression means. So let's go ahead and run the linear model and see what it says. And with a data set that has so few rows in it, the result, the computation is virtually instantaneous. And right away, because all these variables have been standardized, their coefficients are all on a common scale, and you can begin to compare them in terms of absolute magnitude. So a variable like x10, whose coefficient is about 0.46 in absolute value, where you see most of the other numbers are a lot smaller than that, is automatically going to stick out as an important predictor. And I'm afraid I did not do a good enough job mapping the original predictors and all of their different interactions and so on onto the list from 1 to 56 of the predictors. So we're going to treat these variables today in a little bit of a black box fashion, for which I apologize. One should really be thinking carefully about the meaning of all these variables. But ordinary squares regression identifies a bunch of predictors that look important: x1 and x7, x9 and x10, x13, x16, x27. So we see there does seem to be a fair amount of signal. Another way to see that is that the R squared is about 0.87, and so naively speaking, 87% of the variation on the variance scale of the log ozone values is associated with all of the variables that we have here to predict with. And there's some overfitting in that, of course, because there's a lot of variables there that don't really matter, and so the adjusted R squared that penalizes for variables that don't belong drops down from about 0.87 to 0.84, but that's still quite a strong signal. Now, of course, as we talked about last week, this is a nice simple analysis. It has the virtue of simplicity, but every single variable, if you started to do variable selection now, you would start tossing out variables that didn't look like they added very much, and you'd eventually get down to one model that was packed with variables that looked like they really did matter. And that for that variable, the R squared and adjusted R squared values would probably be quite close, and you might consider it job well done from a slightly old-fashioned point of view. But when you're done with one single model, you have a model in which each variable, each X variable, is either completely in the final model or completely out. It has to be completely ignored if it's not in the final model. And in fact, we can do better than that by averaging over our uncertainty about what's the right subset, because then it's a way to have variables be sometimes in and sometimes out, which is a way of having them be partly in the regression, so to speak. And so that's where the Bayesian model averaging comes in that we did last week, and now let's try it again. Last time I showed you a data set with only 6 predictor variables and 1 outcome, and I think we only had 35 or 40 cases, and so the code went quite quickly. Here, 2 to the 56th is a really big number, right? So 2 to the 56th is about 7 times 10 to the 16th. And so none of the methods I'm about to show you are going to be able to do brute force full enumeration of all possible subsets and assign them all posterior model probabilities. In fact, I don't even really know because the people who wrote the code aren't very good at explaining it. I don't know the algorithm that inside the BMA package that Adrian Raftery and those guys at Seattle wrote. I don't know the algorithm that they use for deciding which models to evaluate from a BIC point of view, but you're going to see that the code actually runs quite quickly. And then later on, we'll do the BMS one, which is based upon a Markov chain Monte Carlo search through model space, and we'll see that goes surprisingly quickly as well. So having previously installed the BMA package, I can simply get it with the library command and watch how fast this goes. In about 5 seconds of clock time, it has decided that of those 7 times 10 to the 16th models, only 71 of them are worth paying attention to. And the best 5 models, which it reports here, have a cumulative posterior model probability of about 0.2. And so you can see that 1 over 10 to the 16th is a very small number. And yet with only 5 of these models, we're able to concentrate 20% of the posterior mass. And so these are indeed much better models than you would get just by throwing a dart and picking one model at random from those 2 to the 56th models. And so right away you start seeing, by looking at the posterior probability that the coefficient on the variable is not 0, you start seeing that some of the same variables that we saw in ordinary least squares turn out to be important. Certainly looking for all the ones that have 100% inclusion probabilities is a worthwhile exercise. And so X1, 1, 8, 9, 10, 13, 16, 18. That's about it, right? 13, 16, 18, 42, and 51. Those seem to be the ones that matter. So 1, 8, 9, 10, 13, 16, 18. Look back here. 1, 8, a little dodgy from a least squares point of view. 9 and 10, certainly. 13, 16, 18 is a little dodgy. Looking back, going a bit higher up into the data set, 42 and 51. 42 is not even mentioned by least squares, and 51 is not even mentioned by least squares. So this technique has managed to find variables that have strong value for helping to predict the outcome that weren't even mentioned by least squares. And you have the coefficients on each model, and when there's a dot, of course, that represents that particular variable not being in the model. So you can stare at those and see what's going on. The very highest probability model only has posterior model probability about 0.05, but on the other hand, that's a very big number when you consider that the prior probabilities were all on the order of 10 to the minus 17th. And so quite a lot of posterior mass has stuck to a relatively small number of models. And as we did last week, we could ask for it to give us the posterior means and posterior standard deviations of the coefficients for all these averaging over our uncertainty about which predictors belong and which do not. And we can look at plots and see what's happening. So this is going to give us marginal posterior distributions for the regression coefficients in little blocks of 9. And every time you see, for example, a variable like x1 that does not have one of those vertical black lines in it, that means that that variable essentially always is in the model. Whereas a variable like x3 appears to have a fair amount of posterior probability of not belonging at all because its spike is noticeable. Unfortunately, R has done something not very good for us. It forgot to say what the values were on the vertical scale for the variable x3, so we don't know how big that number is. Graphically, we could work it out by looking back numerically. But a variable like x5, for example, it's a way of saying, because the posterior probability it doesn't belong is about 0.8, it's a way of saying this variable really probably doesn't belong in the modeling at all. And I believe I can get the rest of them just by clicking on the graph. And some of them, like X23, never register anything other than 0 as a coefficient, not belonging whatsoever in the modeling. And then you can look at some others. Some of them have interesting skewnesses to them. The posterior for X30 has about a 50-50 inclusion probability, but when it is in the model, it has a long left-hand tail, so these things don't have to be Gaussians, and so on. So that's the results from the Bayesian model averaging package on a more interesting data set with quite a few more covariates. Now let's go ahead and run the other code. Here I go and get BMS, and I run a command quite a lot like what you saw last week. Just to get a pretty good idea what's going on, I'm going to ask it to run for 1 million iterations, and I think that's going to take us a little while to do. So let's go ahead and do that. Unfortunately, this code does not have anything in it that spits out what iteration it's at every 1,000 iterations or something like that. You just have to wait for it to run for a while. So we'll come back to that in a little while when we see what actually it gets. And I'd like to talk a little bit more about what we did with this data set in the most recent paper that we've been working on. So this paper is written for a technical audience of research statisticians, so it won't be all that easy to read if you want to try to get in there and read it. But we basically have shown that we are able to improve upon a leading method that Bayesians are trying to use for coming up with good prior distributions for finding good subsets of variables. It's a method called expected posterior priors, and we have a way to improve upon them. And we show how our method works, and then we fire our method up on data sets, simulated data sets where we know what the right answer is, and then also on the ozone data. So let's see what kind of answers we got in the ozone data. We used a method which is also used by this BMS. There's a technique called MC cubed, which stands for Markov chain Monte Carlo model composition. And it was invented back in the 80s or early 90s. I guess it was in the 90s by Adrian Raftery and people working with him. And it's quite a simple algorithm that searches model spaces and tries to spend a lot of its time focusing on good models. So MC cubed is worth knowing about. It's pretty easy to program. There's lots of routines in CRAN that have already done the heavy lifting for you to have the programming already done. And we decided to use a two-step process to search the model space. We used MC cubed to identify variables with high posterior marginal inclusion probabilities. And in fact, our threshold for that was any variable that had a posterior model inclusion probability of at least 0.3 was worth retaining in this preliminary step. So we used that as a filter to toss out variables that didn't seem like they were worth looking at any further. And the result turned out to be that we ran the initial list of 56 covariates down to 22 predictors. In fact, I think we have in the appendix toward the back, we have a list of all those variables. And so now you can see what some of the meanings of some of those variables are. Day of year turns out to be a very important variable, but it comes in quadratically to try to create the sinusoidal thing. And so day of year squared is even more important than day of year. And so you'll see that the structure here is basically some things involve cubic terms, some things involve quadratic terms, some things involve interactions, and some things involve main effects, just like you'd expect if you were doing a good job on trying to create a nonlinear surface for your predictions. So I should have done a little timestamp thing to see how long that took. I think it took about 2 minutes. And let me do a summary, and then I'll come back to the coefficients, because the summary is interesting. So it says that it did this million iterations in about 1.95 minutes. So yeah, just around 2 minutes. And in that period of time, it actually visited almost 200,000 models, which sounds like a lot of models, but you remember that the number of possible models is on the order of whatever I said it was before, 2 to the 56th, was it? Yeah, 7.2 times 10 to the 16th right over here. How big is the model space? And so even though it visited 200,000 models in a million iterations, the percent of all the models that were visited was on the order of 3 times 10 to the minus 10th. And so if you really wanted to have it visit a significant fraction of all those models and really explore what's going on here, you'd have to let it run for a lot more than a million iterations. But you'll notice it ran very fast. That's right. Oh, I'm quite confident this is good code. The people who monitor CRAN aren't just accepting any old code and tossing it in there and letting it run. They are applying their own quality control standards on code that's submitted to CRAN for potential inclusion. And in all the years I've been using routines from CRAN, I've found it very rare that there's a routine that is rubbish. These things. We don't, because the routine, in effect, I didn't know how fast it was going to run. And in effect, by giving it a CPU budget of 2 minutes, which was the effective amount of searching it did when I told it a million iterations, it was able to look at a tiny fraction of all the models. On the other hand, its method for deciding where to go next tries to have the property that it will generally tend to visit good models more often than bad ones. And so we can hope that if you took any length of time you thought of, let's say we contemplated running it for 24 hours, and you let it run for the first hour and compare its answers with what it got by running all 24 hours, you would find that a lot of good models have been front-loaded in that first hour. So it's not as though it needs the other 23 hours to really find a bunch of other good models. Its sampling technique tends to oversample on the good models and then reweight them back based upon how many there are to look among. So it is true that we would find if we ran longer, and 2 minutes is pretty fast, and so if this was a problem that I really cared about, I might well let my laptop run overnight, for example, and see where it got, or even a day. Let's make a little calculation. If it's only visited, let's call it 1 times 10 to the minus 10th. Well, let's do it like that. So suppose I take 2 minutes and divide by 2.7 e minus 10 to see how long it would take to apparently visit them all. And the answer was it would take that many minutes. And that's a long time, right? We could divide by 24 times 60 to see how many days, I guess. So let's do that. And it's about 5 million days. So you're probably not going to get there. This code is a lot faster than some code I'm going to show you in a little while that was written by my colleague Thanasis Kotas at UC Santa Cruz, because his code is wholly within the R language, which runs quite slowly. What this guy has done, whoever wrote BMS, is he has R functions that serve as a wrapper, basically, and then he makes direct calls to C++ functions or things written in Fortran 77 or some other fast language. So this This would be hard to make faster. We could parallelize, but even with a Hadoop cluster with 8,000 processors in it, if things scaled linearly, we would still have to wait 2 years, or yeah, about 2 years to get something approaching having had a chance to look at all the models. So these are big model spaces, is the point, and we can trust the fact that this particular algorithm was set up to front load good models. Okay, so. Unfortunately, this sort of technology does not come well prepared to answer that question. One thing you can do, it does create, as I showed you last week, it does create log scores based upon the quality of its predictions. And so you could, if this, again, was a data set that really mattered to you, you could run it for an hour and get a log score value for some data that was held out. And then, independently of that, in parallel, run it for 4 hours and get the log score on the same held out data and see if the log score had measurably improved. And I'll show you later on next week, I'll show you a method for, maybe even later today, for calibrating log scores, so you get a chance of understanding when is a difference between two log scores big enough to matter. So that would be one thing I would think of trying. But the technology itself is not automatically suited to helping answer that question. It's a very good and natural question, but this guy didn't think along those lines. All right, let's see if it can do anything else for us. Well, we can start looking now and see which variables it thinks are important. And you'll notice that by asking for the coefficients, it automatically sorts them from apparent best, most important, down toward the least important ones. It's getting some of the same variables that we saw BMA did as big ones. 1, 10, 16, 9, 8, 13, 2. That should be vaguely reminiscent, right? 1, 2 has 97.6. 1, 2, 8, 9, 10, 13. So these methods are producing similar subsets of really important variables. If you studied this for a while, you would see, though, that just as was the case with the BMA approach, this approach is uncovering other variables that were not discovered by least squares as worth paying attention to. I can ask it to summarize the first 4 top models, for example. I could run that command, and it will create a little matrix of 1s and 0s that shows me which variables appear in which models. The very highest posterior model probability model had 1, 2, 7, 8, 9, 10, 12, 13, 15, 16, 18, 20, 43 in it as its predictor variables. That's considerably less parsimonious than the sort of story that this BIC-based approach was getting. The very best model it found had only 13 predictors in it. And if you look at its best models, they have 13, 11, 12, 16, 15 as its number of predictors in it. If we look down at these, we'd find that almost all these models have more predictors than that. So what I'm learning empirically, and this could be verified by looking at the what's actually going on underneath the hood, I'm thinking that the BMA software, based on this thing BIC, has a bias toward more parsimonious models, and the BMS technique, which is using a different criterion for deciding when variables matter or not, has a bias toward less parsimonious models, which will tend to lead to better predictions. I think that's what's going on here. So, and I told you a little bit about that Rubicon last time. I'm going to say quite a bit more about it later today. If you want to find a model selection technique that has the property that in the space of models that you agree to look around in, there is the right model, the so-called true data generating model, at least as far as structure is concerned. If your attitude is, I want a method that will concentrate more and more posterior probability on that model as more data accumulates, that's what's called paying attention to consistency of the model selection technique, then BIC does a good job for that. But if instead your goal is finding models that have good out-of-sample predictive performance, that will tend to involve models that are a bit more complicated than the ones chosen by BIC. And you may well not have the kind of consistency that you get from BIC, but you may have models that predict better. So there is a basic trade-off in finding a technique to compare models along that line, and I'll have more to say about that later. Notice that the posterior model probabilities that this technique is getting are much, much smaller than the ones from BIC, and that's because it's visited so many more models. And so it's normalized over a much larger denominator. I don't understand. I would need to read. It's making a comparison here between the MCMC posterior model probability, which is based upon how often that model was visited, I suppose, across the million iterations, and something called exact. And I find that remarkable, because if they had an exact way to compute that, why were they doing the Markov chain Monte Carlo? I would have to read this guy's documentation and maybe even look at his code a bit more to see what's going on right there. And then we can do one last interesting picture. This picture shows the prior is in dotted lines in red, and the posterior is in solid lines in blue. What it shows is when it began, it was giving all those 2 to the 56th models equal possibility, and therefore the prior has, on the number of elements and the number of predictive variables in the model, is centered at around half the number of predictors. And what you see comparing the prior and the posterior here is that quite a lot of learning has occurred, because the posterior is noticeably different from the prior, and it's in the direction of finding models that are substantially more parsimonious than simply throwing a dart into the 56 space and getting a model that has quite a lot of predictors in it. In fact, the mode of this thing seems to be at about 16 or so. Hard to read on the scale here. 16 or 17. I think, in fact, back here it said that the mean number of regressors that it looked at was about 17, and that matches the mode pretty well, because it's pretty close to Gaussian. So yes, I think everything I've said so far would hold up under additional scrutiny on my part. The BIC approach is finding rather more parsimonious models, and the BMS approach, that was BMA, more parsimonious models, BMS, less parsimonious models, and I'm going to guess that those models are going to predict a bit better. It might go to those places briefly, and then move right away from them, because there is a sense from even just looking at the ordinary least squares results that there's a fair amount of deadwood in our list of 56 predictors. And so you wouldn't want to hang around too long up in deadwood space where you have several dozen variables that don't really add very much. I'm afraid I did not. Yes, very natural and important question. I'm afraid I did not have enough time to explore that. And if I were talking to the developer of this method, I would say that was something that I think it's a he should program in automatically. It should just come right out, because it's easy enough for him to fit the ordinary least squares model and make out a sample predictions. So what he should do is, just as an automatic button push, you partition your data. We might take the 330 days that remain and randomly sort them, because at the moment I think they might still be in day order, for example. and hold out 50 of them, for example, and see how well the modeling does on that. And I like your question a lot, and I intended to do it, but I ran out of time, so I'm going to make another note to myself to try to get that done for next time. That's right. How much better are we doing predictively by being prepared to average over many, many, many models? That's exactly right. Okay, so that's what I wanted to show you about that example. There's also some new Bayesian nonparametric stuff, new since last week, that I have prepared for you. In fact, let's look first. What I showed you last week was how Dirichlet process priors work and how prior to posterior updating goes in a situation where you aren't actually having to worry about the parameters of the centering distribution. So what am I talking about? Let's go over here. I'll try writing in this world. So you remember the basic story that Dave Finetti said, if you have exchangeability, then you have to begin thinking about the population CDF, and if you knew what it was, the YIs would be IID from it, and then you have to be prepared to place a prior on that F. And that prior has two ingredients you have to specify, either from the DP Dirichlet process point of view or from the polytree point of view. Both of them require you to specify something that behaves like a prior sample size, N0, and something that behaves like an F0. All the examples I showed you last week, F0 was a single member of a parametric family. For example, the normal distribution with mean 0 and standard deviation 1. That's not realistic in practice because generally the scale of the Y's will not have mean 0 and standard deviation 1. It will have some other scale. The location will be other than 0 and the scale will be other than 1. And so what we would really like to do is to center the whole thing at not the normal 0, 1, but the normal mu sigma squared family, and then learn the mu and the sigma squared from the data. So our goal in the Bayesian nonparametrics is to try to learn these as well as learning F in terms of its basic shape. We also want to learn these parameters that govern the behavior of the normal distribution that's the closest to the actual data generating story. And so the models I showed you last week, while they were interesting as a place to begin understanding how Bayesian nonparametrics works, they weren't fully realistic yet because we are generally going to be wanting to write down models in which the centering distribution is itself not a single distribution, but it's actually an entire parametric family. Then we have to learn the parameters as well. And so that involves going from Dirichlet and polytree models to Dirichlet and polytree mixture models, in which we mix over our lack of knowledge of the mu and the sigma squared. And that, incidentally, as I mentioned to you last week, that will fix the problem that the DP has of putting all of its mass on discrete distributions, because that mixing process will create a tremendous amount of approximate continuity in learning about mu and sigma squared. And so we will be able to get arbitrarily close to continuous distributions if that's what's really going on as well. So let's look at Thanasis' code first. It's easiest to talk about, really. Oh, thank you. Yes. I'm really not very good at that. So here's some code he wrote a few years ago when he and I gave a short course on Bayesian nonparametrics. And as I said, it's completely valid code, but it's slow because it does all the work completely inside R rather than calling outside of R to a routine in C++ or some other fast environment that does the heavy lifting. It does all the heavy lifting inside here. Then he wrote a little file about giving information about how it works, and then also he created some simulated data that we can see. Basically, what this program does is it fits something called a location normal Dirichlet process mixture model For people who like acronyms, that runs out to LNDPMM, which is an acronym you see in the literature. You could go look at it on your favorite browser, and you would find that there's lots of stuff about that. So what's he saying here? Well, he's saying, let's suppose that each observation, so we have a single vector of real data values, y sub I, and if we knew some number theta I and we knew some number phi, the y sub i's given theta I and phi would be independent draws from a normal distribution where each yi is allowed to have its own mean, theta I, and then they all have the same precision, phi. Or perhaps on his scale, phi is a standard deviation or a variance. We'll have to look at his details and say what's going on. Yes, in fact, it's an inverted gamma. It's given an inverted gamma prior distribution, so that's a variance. So this is already an interesting model because the top level of it has far too many parameters, right? Because it's like fitting a separate normal curve to every single observation where everybody is allowed to have their own mean. And so the top level of this model is impossible to fit because we have n observations and n plus 1 parameters. Everybody has their own theta, and then you have an additional variance parameter. But we make the model fittable by going on to say, well, it's not that everybody has their own theta. Instead, just as we did with those random effects models for talking about meta-analysis, we say it's not quite that everybody has their own theta. Everybody has sort of their own theta, except all those thetas are similar to each other. In other words, our uncertainty about any given person's theta I is exchangeable with our uncertainty about any other person's theta I. And as usual in the Bayesian story, we can make that idea of exchangeability operational by regarding them as all IID draws from a common distribution. So that's where the usual random effects move comes in, where we say, we start out by letting everybody have their own theta, but that's too many parameters. Now we say, well, actually, it isn't really true that everybody has their own theta. We expect all those thetas to be similar to each other, and let's implement that by having them all behave like IID draws from the same distribution. Now, if we pretended that we knew that G was normal, then we'd be back in the world of that normal random effects meta-analysis model I showed you before. But why should we pretend that that's normal when, in fact, we don't know what it is? And so the position taken by this particular Bayesian nonparametric model is to say, let's take G as something we don't know, along with phi, for example, or phi, and try to learn it from the data. And so let's put a nonparametric prior on it. So G is a draw from a Dirichlet process with parameters alpha and G0, and alpha plays the role of the prior sample size, and G0 plays the role of the centering distribution, or the prior estimate of what the underlying G is. And now we're going to let the G0 itself be a normal distribution. So we're going to center this Dirichlet process at the normal, which is what we would have done. We would have put all our eggs in the normal basket if we were fitting that previous random effects meta-analysis model. But now let's relax that assumption and allow that distribution to be unknown, but centered at the normal with unknown mu, mean, and unknown variance, tau squared. And we don't know what alpha is either, because alpha, it turns out, is a funny thing in the Dirichlet process. Its meaning is mixed up between two different ideas. One is something that behaves like a prior sample size, and if all it were a prior sample size, then in fact you can't learn something like that from the data because it's a prior sample size. You're supposed to stick that in yourself as something that's independent of the data set. But in the Dirichlet process, alpha also stands for the following idea. Do the data values in this model, do they tend to cluster? For example, if the distribution were bimodal or trimodal, then the data would start to cluster, and alpha keeps track for you automatically of the number of clusters that the data are exhibiting. And so from that point of view, alpha is something that we ought to be able to learn from the data, because we don't know at the beginning what the number of clusters is, and alpha will tell us how many that is, and thereby we'll be able to learn about it from the data. So now we have to put priors on the remaining things in this model. So we put a prior on phi, and the standard conjugate prior is to have it be a an inverse gamma distribution with particular hyperparameters a dot phi and b dot phi that we have to specify as users. And then the alpha and the mu and the tau have to have priors also. And the standard thing to put on the number of clusters thing in the Dirichlet process is a gamma distribution. And then it would be natural to express whatever you may know about the mean of the centering distribution by putting a normal prior on it and then an inverse gamma again on that variance parameter for the centering distribution. So this is like a complicated machine in which it's a box that has 8 dials on the outside of it. You get to play with the a dot phi, b dot phi, a dot alpha, b dot alpha, a dot mu, b dot mu, a dot tau squared, b dot tau squared. Those are your 8 inputs as a user to this machine. And based upon how you set them, an answer comes out the other side using Markov chain Monte Carlo. And it's either a good answer or a bad answer according to what you put in for those 8 numbers. And you can sometimes make it a better answer than what you would get by looking at the data a different way by choosing those 8 numbers quite carefully. And so that would be a situation where Bayesian nonparametrics is doing a particularly good job. And the way Thanasis wrote his code, the only aspect of this that he's really interested in is working out the Pasteur predictive distribution for a future y value from this model. And the reason he's interested in that is if you think about what that would look like, once you draw it, that actually represents a pretty good density estimate of what the actual underlying density is that the data came from in the data generating process. So he's pretty interested in the Pasteur predictive distribution for a future y value, and he's going to use that as a density estimator. Of course, we have other density estimators at our disposal. One of them is called the histogram, so we could make a histogram. We also have another one available inside R. It's called the density function, which does kernel density estimation as a kind of smoothing operation. So it'll be interesting to see how this machinery does at recovering the population density story, having not been told what that story was to begin with. I see it's time for our first break, so we're going to break now and come back at 10:15. And so VC Ops, we can turn things off now, right now, and turn back on at 10:15. Thank you. So, looking again at the file that Thanasis created to help us understand how his code works, I've described the model to you now, and now let me tell you about the code that he wrote. Clearly, we're going to have to input all 8 of those numbers I mentioned before. And you can see they're all right there in his input vector. A alpha, B alpha, A mu, B mu, A tau squared, B tau squared, A phi, and B phi. Obviously, we're going to have to input the data set, the data vector itself, Y, as well. And then, of course, to run the MCMC, we need to tell him how long to do a burn-in and how long to do the monitoring run. And so he uses the symbol IB to stand for the number of iterations in the burn-in period, and capital B to stand for the number of iterations in the monitoring period. And as I mentioned before, the choice of those 8 hyperparameter values can have a lot to do with the answer that you get. The example we're about to run the data on has 250 observations in it, and it was simulated as a mixture of 3 normal distributions, one that was centered at -5, one that was centered at +3.5, and one that was centered at 0, with half of the weight in the middle and the other weight distributed approximately equally in those 2 distributions farther away. And the variances were all chosen to be 1 in this mixture. So what you find is you're going to get 3 quite distinct modes in the data. And if this Bayesian nonparametric machinery is any good, this will be a decent test of it, because we're going to center things at the normal distribution, which has only 1 mode, and then try to learn what the actual story is from the data. And so as I showed you last week in the Dirichlet process, in effect, it is going to behave like a generalization of the bootstrap, in which every time it makes a draw to simulate the future data value, it's a you toss a coin, and with a particular probability, you sample an existing data value, and then you toss, with the probability 1 minus that, you sample a value from the prior centering distribution. So 250 observations means that we're going to have a fair amount of data to try to learn the actual data generating capital G. But you do have to exercise some care in choosing these hyperparameters. N star is the name that people give in this literature to the number of clusters. And Thanasis has chosen these A alpha and B alpha values as inputs to the inverse gamma distribution in a way that yields an expectation before the data has been seen that there might be somewhere around 6 clusters in the data with a give or take big enough that the number of clusters could be all the way down to 1 and all the way up to about 10 or 15. So we're basically putting in a relatively diffuse prior on the number of clusters and letting the data tell us. And let's continue to read what he says. He's chosen values of these parameters that yield infinite prior variance for the tau squared and the phi. I personally don't support that sort of choice for reasons I've said to you before. There will never be an infinite prior variance, but that's like having a prior precision that is very small. So that's a way to try to produce something that is quite close to low information content on those things. There is something that people in Bayesian nonparametrics do that sounds a little bit like using the data twice. They often choose these hyperparameters in a way that gently is influenced by the actual data values to give the sampling a chance to find where the posterior is in the space of possible values. So for example, marginal prior moments for y that correspond to rough prior guesses of 0 for the center and 14 for the range of the data. So expecting the data to be somewhere around 0, going around 7 units either way. And he got those numbers by looking at the actual data set to decide where to approximately center the prior and how much variability to give. People who think that the Bayesian story should always make a complete separation between the prior information external to the data and the data information internal to the data set. If you're one of those people, you have a right to be a little bit offended by this because you're actually using the data to set the prior. But it's actually quite a gentle way to do so. And if you used values that were not so directive, the sampling would eventually find the right mode anyway, but it would take a much longer burn-in period. So in effect, what you're doing is you're putting in hyperparameter values that help to make the burn-in a bit shorter than it would otherwise have been. Okay. And then he does a few more calculations to see how those things should be set. And he points out the following thing. Sensitivity of posterior predictive inference to the prior specification can be studied by considering other prior choices. And so he's suggesting to you, if you don't like the way I did it, you can try other values yourself and see if you get better answers than mine. His code is a little bit profligate in the way it writes out answers. In whatever directory the code is running in, it writes out 8 different files. So it writes out a file for the alpha, the posterior distribution for the alpha, and for mu, and for tau squared, and for phi, and for n star, which gives us a sense of how many clusters there are. It creates a file called posterior predictive distribution for theta. So that would create a predictive distribution for a new theta associated with a new observation. And then finally, the files prior predictive y.txt and posterior predictive y.txt include samples from the prior and posterior predictive distributions for a new observation coming along after we've seen the data now. He calls that new observation y0. And so at the end of the code, what we're going to do is we're going to plot the histogram, and we'll plot the prior predictive over top of it and the posterior predictive over top of it. And the prior predictive, you will see, is quite far from the histogram. And then the posterior predictive turns out to have learned the actual density shape quite well. So like he says down here, a density plot based on the sample in posterior predictive y.txt provides the Bayesian density estimate arising from this DP mixture model. So let's go ahead and run the code. I believe I downloaded this stuff into a directory already, so let's go there and see what's there. I ran it earlier this morning, and so there's a bunch of files already there. But if the files exist already, his code will simply nullify them and write over top of them, so no problem there. So I want some code called running kotasexample.txt, and I'm going to need also a file that represents what his code actually looks like. So what's this here? That I can go ahead and recycle. It's here. That's the ozone data. I can recycle that. Go back to the course web page and download the code again. So here's the code. Let's go ahead and save that to the so there's his code. It's called lndpmm-code-r.txt, and I have to look in my code to see whether that's what I need it to be called in order to work well. So let me download also the code that I wrote to run his example. Yes, it wants the actual code to be in a place called lndpmm-code-r.txt. Let's go ahead and see if I can do the following. I'm going to put that there, drag and put that there. And now I believe everybody's where they need to be. And I can run the code now. Go ahead and so I'm going to start up an R and change directory. My instructions here say to myself, change directory to where the code and data files are. So that's going to be this place here. That should do it. And I'm going to go ahead and source his code, read in the data, and get all the hyperparameter values assigned. Looks like all that worked. I can check by seeing if his program MCMC was loaded, and look, it's all there. I'm happy. Then I want to unbuffer the output so I can watch the iterations go by. Thanasis is not the world's greatest R programmer, and so in his original code, he actually printed every single iteration out, and that spends a great deal of CPU time just writing needlessly to the screen. So I did the usual little thing in here that causes it to only print out every 100th one, and that will save us some CPU time. So now let's run his code. And learn this data set. And so because it's in R and not porting out to C++ code, you can see in front of you here that it's taking quite a long time to do its work. So maybe we'll go away and look at something else in the meantime. What did I tell it to do? I told it to use a burn-in of 500 and 2,000 monitoring iterations, so that's not that bad. It's already started the monitoring. While we're waiting for that to finish, let's see what else I'll orient you to what else is here. Part 1, Part 2 are the sampling from the prior and sampling from the posterior without the mixing over parameters, code I showed you before. This one here, I'm going to show you today how to use routines from the DP package that comes from CRAN that does Dirichlet process and polytree fitting. One of the authors of that package is called Tim Hansen, a very good Bayesian nonparametric statistician, and he wrote an alternative way to do this sampling in polytrees. Actually, in WinBugs, he figured out how to trick WinBugs into doing Bayesian nonparametric sampling. And he gave me two different versions of the code, one that monitors the underlying median of the process and one that monitors the underlying mean of the process that you're trying to learn about. So we have two different versions of his code. And then the rest of what's here you know the meaning of. Okay, so it now has finished a burn-in of 500 from some starting values that it generated from the prior that was specified here, followed by a monitoring run of length 2000. And we're ready to go ahead and see what the results are. So first I'm going to bring in those two files and draw for you a histogram of what the data set looks like. And so the intent here was to create a data set that was multimodal, and you can see that he succeeded in that regard. And in fact, there do appear to be three local modes, one at about -6, one near 0, and one at about +3, so something like that. And I will now show you what the prior predictive distribution looked like. And the answer is a normal curve, a single normal curve centered at 0, and having a standard deviation big enough to accommodate the basic spread of the data. So that's what the Bayesian nonparametric inference engine started with, in its opinion of what the density of the data generating process looks like. And with only 250 observations and the prior that we used, it has now learned the truth to the following extent. The posterior predictive distribution, this is a density trace of a bunch of draws from the posterior predictive distribution. And you can see that, in fact, it has picked up correctly the fact that the true data generating process is trimodal. And if we look back and see what Thanasis said in his information, the data generating process had a mode at -5, a mode at 0, and a mode at 3.5. And in fact, if we drew the bars a little bit differently, you would have seen that, yeah, look, the mode is estimated at -5. This one's estimated at 0, and this one's estimated pretty much exactly 3.5. So with 250 observations, quite a lot of learning has occurred because you can compare the prior centering distribution to the posterior density inferential distribution, and we've been able to recover structure that was not put in the prior. So this is an example of successful learning in a fully nonparametric fashion of what's going on. Now the lawyers always say, if you ever talk to them, they always say when you're cross-examining somebody during a trial, never ask someone a question that you don't already know the answer to. And the analog of that here, trying to run a course like this, would be never do something in showing people how code works that you didn't already practice beforehand. But I'm about to break that rule because I notice now, having looked back at this particular directory, that in addition to writing out the prior and posterior predictive data sets, he wrote out a bunch of other things as well. For instance, he wrote out mu.txt, and so why don't we take a moment to read in and let's make a density trace of that. Plot density mu.star and see what it thinks the posterior distribution looks like for the mean of the underlying process. I was expecting this distribution to be quite a bit lumpier than that, but this is probably a consequence of having 250 observations instead of a smaller number, which I'm about to show you in another example shortly. What we begin to see when we fit Bayesian nonparametric models to data and then look at summaries of the population CDF, like the mean, for example, we begin to see some fairly shocking things, that the posterior distributions, which we're used to seeing as quite smooth things, actually end up being quite rough looking. And that's because the smoothness was imposed by the parametric assumptions. And of course, you don't know that the parametric assumptions are right. You're just hoping they are. And along with them comes the smoothness that we've come to expect in looking at posterior distributions. So that is an interesting thing to have looked at. And I guess we could look at the n star, for example, and see what that looks like. I'm going to call it n star star. Now, did he call it n underscore star? What did he call it? Yes, he likes underscores. I'm not a big fan of them myself, but so be it. And so you remember that the prior was on the number of clusters was centered at about 6. The posterior is also centered at about 6. In fact, we know that there are really only 3 basic modes, but in fact, the way the Dirichlet process works, it is allowed to regard itself as having more than 3 clusters in order to create 3 modes. And so basically, the number of clusters tends to track as a number that's larger than the number of modes. So you can experiment with that code on your own time if you're interested. Basically, you have a chance to mess around with the hyperparameters and then look at all the files that come out and sharpen your understanding of how the Bayesian nonparametric story actually works. So I'd like to spend a few minutes now showing you how to use some of the functions in DP package. Despite its name, as I mentioned a minute ago, it fits not only Dirichlet process mixture models, but also polytree mixture models. And so here's a rather long file that I wrote that we're going to look at now. I can get rid of that now because I have Okay, good. So let's fire up another R. I believe everything inside this file is self-contained. If you are going to do this for the first time, you have to install DP package from CRAN. I've done that already in mine, so all I have to do is to hit it with the library command to get it to be loaded. And then I have to remember to unbuffer the output. What I'm going to do now is show you a polytree analysis of the NB10 data set that we looked at from a parametric point of view earlier this quarter. So let's go ahead and bring in DP package and the NB10 data. Recall this is that data set that has a pretty long tail in both directions because there were outliers in the left and the right tails both. Let me unbuffer the output. If I were to do a histogram of Y, you would see that it has a pretty long right-hand tail. If I did a QQ norm of Y, you would see that it's showing symmetry, but it's got substantial outliers in both tails. We looked at this data set parametrically some weeks ago. In fact, what we did parametrically was we modeled it with a t distribution with an unknown number of degrees of freedom, and we found that the posterior on that degrees of freedom parameter was centered on quite small values, around t on 3 degrees of freedom. So pretty heavy tails. I'm about to run a function called PTLM. The LM part stands for linear model, and the PT for polytrees. So we should take a moment and see how this function works before I actually run it. I'll bring in a bunch of the inputs that it needs and specify all of them. On the course web page, one of the things that I have loaded for you is, back under today's date, we have documentation for DP package. And I'm going to go ahead and save that to the desktop so that we can continue to look at it here. So the developers of this package, the principal developer is a guy from Chile named Alejandro Jara, and he's a very good statistician. He helped me quite a bit in using his code to write that book chapter that I showed you a little bit before, and we're going to look at it some more today. And then Tim Hansen, I mentioned before, is one of the co-authors. Fernando Quintana, another good Bayesian nonparametric statistician. Peter Mueller, another good one. Gary Rosner, another good one. So there are 5 different people who have all been involved in writing this code, but actually Alejandro is the main person on the routines that I have used so far. And unlike many software developers, he will answer his email about his package. He will actually help you when things go wrong. And they update it all the time. The version that we're going to look at now was actually revised only just about a month ago. So there's a lot of functions in it, of course, and the one we want for now is PTLM. And so does it work this way? Can I click on that and go right there? Isn't that nice? Look at that. That's PTGLMM. And so it says, this function generates a posterior density sample from a semi-parametric linear regression model using a mixture of Polyetries prior for the distribution of the errors. And then it tells you how to run the function. You have to give it a formula that defines the linear model you have in mind. I always let that default to the value that's in there built in. I leave that alone. But then we have to specify lots of stuff to make this thing go ahead and work. And I'll be telling you how to do those things as we go along. So first, let's go and see what model that the code has in mind. Look at the equation at the bottom, page 232, right here at the top of this screen. The part that goes yi equals xi beta plus vi should remind you of the standard way people write the multiple linear regression model in matrix and vector form. And the vi is usually taken to be a symbol that usually involves either the Roman letter EI for so-called errors or the Greek letter epsilon also for errors. But they choose to use VI here for some reason. So we have an opportunity to fit a regression model, y equals x beta plus e, in this case plus v. And the standard assumptions of the regression model, as you know, are that y equals x beta plus e, and the e vector is regarded as consisting of a whole bunch of IID normal 0 sigma squared random draws. Something that you would immediately want to try to remove as a hard and fast assumption in regression, if you wanted to try to do better than the standard regression model, is to say, well, where does that normality assumption come from? We just usually put it down because Mr. Gauss did it first around the year 1800, and he got good answers, and it was easy for him to do, and so on. So we often like to assume the errors are Gaussian in regression models without knowing that that's true. And so now that you know the Bayesian nonparametric perspective, what are we going to do instead? We put a Bayesian nonparametric prior on the distribution function of the errors centered at the normal distribution. So the second line of the model says, okay, if you knew what the right G is, if you knew what the right capital G is, the VIs, the errors, would be IID from G. And then you put a Bayesian nonparametric prior on G. In this case, rather than using a Dirichlet process, Alejandro uses the polytree. And again, not a polytree just centered at a single distribution, namely, for instance, normal 0, 1, but a family of distributions. And so the symbol pi, capital Pi, with the sigma squared in the superscript means that the polytree is centered around a normal distribution with mean 0 and variance sigma squared. That's the usual distribution we would use for Gaussian errors in a regression model. And all the other words here, I hope you'll find familiar from the introduction to polytrees I told you last time. By taking each m level of the partition to coincide with the k over 2 to the mth quantile of the normal distribution. I showed you how to build the tree last time. And the family that loads in the prior sample size was specified exactly in that way I showed you last time. You have a number alpha that you get to choose as a tuning constant as a user. I called it C last time, but here he's calling it alpha. And you have to make those alphas get big faster and faster as you go down different to lower levels in the tree, where m is tells you what level you are in the tree. And so a standard choice to make everything behave properly to approach a continuous story with a lot of data is to make it go like alpha times m squared. And so now, as a user, you have to put in either a single value for alpha or a prior for it. And then you have to put in either a single value for sigma squared or a prior for it. And the standard assumptions that are built into this are that just like in the Dirichlet process, you're prepared to think of alpha as like a draw from a gamma distribution. You can, of course, choose these A0 and B0 in such a way that this corresponds to putting all the point mass on a single value. In fact, there's another way to do that in his code as well. And the standard conjugate prior for a variance is to have the reciprocal of the variance follow a gamma, or in other words, the variance to follow an inverse gamma distribution. And then you get to put in the hyperparameters tau1 and tau2. So it's quite a bit like what we just saw, except now we're allowing the basic structure of the data to involve regression. So that's why this is called a semi-parametric model. It's partly parametric in the way it assumes how the x's relate to y, namely in a completely linear fashion. So that part's parametric. And then it's Bayesian non-parametric on the errors. That makes it what people call a semi-parametric model rather than a truly Bayesian non-parametric model. If we wanted to try to be truly Bayesian non-parametric on the whole model, we would try to put down some kind of process here for the mean that allowed for some nonlinear structure to be learned from the data as well. And that's starting to get kind of hairy because if you put a Bayesian non-parametric process for the mean and another Bayesian non-parametric process for the noise, those two Bayesian non-parametric processes are going to start competing with and interacting with each other in ways that might be strange, in a manner somewhat similar to the thing I told you about with the people with in-home geriatric assessment, where people are going to different doctors and getting different medicines, and then having those medicines create a little war in their bodies. You might, if you tried to put down what's called a Gaussian process here to be completely non-parametric about the nature of the regression surface, and also a Bayesian non-parametric prior right here, I think you would discover that you have written down a model that had too much freedom in it. It's something like saying that you have something that's over-parameterized. But we're not going to do that today anyway. We're just going to hold the x beta part constant. In fact, I have a data set that doesn't have any regressors at all. And so I want the x matrix just to consist of a vector of ones to correspond to a regression with only an intercept term. And so, in fact, if you look in my code, it wants to know what the formula is for the regression process. And I'm going to say the data values are distributed as they come from a model in which the only predictor variable is the vector of ones. And so that's going to create a model where there aren't any predictor variables at all, and we're just working with the one sample story, and I'm trying to learn about the mean of that process. Okay, here's where I am. Now, by default, his function doesn't work with the mean. It works with the median. And so I'm going to be learning the median of this data set. But because this data set is symmetric, I expect the median to be quite a lot like the mean. And in any case, he has a flag that you can use. If you say that this particular flag is false, then you get a mean regression model instead, and you have a slightly different structure for how things behave. But I'm going to run it in the median regression setting. Because when I first started working with this stuff, Alejandro's code for this switch equals false was broken and didn't work right. So I'm going to show you the results with working with the median here. It may be that with this most recent release that this particular thing works now. That would be great if true. I'll explore that over lunch, I think, for us. But that's just a consequence of his code not working for something that I wanted to do. I would rather, you're right, I would rather use the mean. Okay, and so what you need to know as a user is how you specify these hyperparameters in the same way that you needed to know that for Thanasis' code. There's a bunch of other stuff you have to tell it as well. You have to tell it, so here I'm going to take the NB10 data as it came to us, and I'm going to sort it from smallest to largest. Doesn't hurt to do that. Then you have to tell it how long the burn-in is. I'll use 5,000 burn-in iterations. Then you have to tell it how long the monitoring run is. And here, what I chose to do is to have 10,000 saved values with a thinning ratio of 20. Alejandro's terminology for that is skip. And skip, and if this were set to 1, you would store every iteration, but if it were set to 20, then you only write down every 20th iteration. That will thin the output, and it will also create a smaller degree of autocorrelation in the output than you would get if you wrote every single one out. And I think this thing says how often it should report back how many iterations it has finished. So first I create a vector of MCMC control parameters. So I tell it how long the burn-in is. I tell it where to save the output. I tell it how much, I tell it how many monitored iterations I want. I tell it what the thinning is, and I tell it how often I want it to report iterations. So that's just a kind of technical thing that tells it how to run the MCMC. Now, in this first run, I used the following syntax to tell it what the prior actually is. I force alpha to be identically 1 rather than putting a distribution on it. And we go back to the code now and see what's going on here. So just a moment while I remind myself how this works. Yes. So you're allowed to put in information about the regression parameters. In my case, it's just going to be the regression coefficients, and that's the thing I'm interested in. So I'm going to be wanting to put in prior information that looks like what's going on in the example. So in the example, they have also set alpha to be 1. They have a regression where there's 2 predictor variables and an intercept. So their beta vector has 3 components to it, and they center their prior at 0 for the prior distribution on the regression coefficients, and they give the covariance matrix for the regression coefficients that has actually it's a covariance matrix, not a precision matrix, and so it has really big numbers saying that we don't know much about what those quantities are. And then I put the usual gamma, epsilon, epsilon sort of priors on the gammas, and I say capital M equals 6. That forces it to build a polytree down to 6 levels, as I've shown you before. So since I have a regression with no predictor variables, the beta 0 thing is just going to be basically saying my centering distribution on the mean, or rather the median of this process, is going to be a normal distribution centered at 0, and with a really big variance, which is going to correspond to very small precision, and I put in quite non-informative values or low information content values for those guys as well. So we can go ahead and run this now. I say formula equals just fit a regression with no predictor variables. Bring in the prior, bring in the MCMC. Let's see. Where did I create something called, oh yes, I just called that thing as a null vector for state, and status equals true are just some things that it always wants to know. So what have I told the R session so far? I told it all the way down to the prior. So let's go ahead and run this guy. And I think what we're going to find is that 200,000 iterations thinning every 20 on my particular processor takes about a little bit under a minute. I remember, yes. And so compare this with how fast Thanasis' code was running, very much like a snail compared with this. And that's because, as I said, Alejandro is calling a C function or a C++ function from inside R to do the actual heavy lifting. So this is going to take about a minute while it does that. Does anybody have any questions or comments about the Bayesian nonparametric story? Uh-huh. In fact, we learn. I mean, we run into situations all the time where the error distribution doesn't look anything like a normal distribution at all. In particular, I know for my problem that the error distribution doesn't look normal because that would be like saying the actual distribution of the data follows a normal curve. So this is a way to ask it to learn what the underlying CDF is instead of imposing the normality on it. And in general, with regression, the errors often have outlying observations that make heavier tails and the residuals in the regression. Also, they can be what's called heteroscedastic, meaning that some of them have larger variability than others, and that will not be taken up correctly with the IID normal assumption, where every particular error has a constant variance. Heteroscedasticity is not something that this code is prepared to fix, but there are other versions of the Bayesian nonparametric story that would help to fix that. So this thing is finished now. We can begin to explore what it got. I can run a summary of the object that I just stored it in, and you'll see that it has worked out a variety of things. It tells me about the various summaries of the posterior predictive distribution on the log scale. And it begins telling me regression coefficients, both mean and median. So evidently it's able to focus both on the mean and the median, even though I was implicitly only interested in the median. You'll notice that mu would have been the coefficient for the vector of regression coefficients, but because the intercept term is standing for the vector of regression coefficients, the way the code has dealt with that is that this thing called mu is simply dummied out completely, and it has every summing 0. So the thing I want is to look at the result for the intercept, and so it's saying basically that the posterior mean of the center of this distribution is at about 404.2, which is a lot like what we were getting from the parametric modeling. For instance, if I do a mean of the y values, I get 404.6, but the t distribution we were working with before was getting a number like 404.2. The posterior standard deviation of this quantity is about 0.59, and that's smaller than the answer you get from pretending the data are Gaussian. The right Gaussian answer is about 0.6 something. So it has done a little bit of learning in moving away from the answer you would get from the Gaussian. The t answer is much smaller. I remember that the t answer here is about 0.45, and so we've moved part way away from the Gaussian, which was the centering distribution, toward what the data has to say. But with these particular parameter values in the prior, it hasn't been able to fully learn that yet with 100 observations. And it shows the 95% interval. And now we're ready to actually go ahead and look at at the output. Um, these things here, I forget if I've told you before, we talked about how metropolis sampling works. It turns out that the optimal acceptance rate for one parameter at a time in the metropolis sampler is about 0.4 or 0.45 or so. And so these numbers are actually quite close to optimal, just as a function of what has been done already without me fiddling around with the MCMC. So his code seems to have produced a fairly efficient MCMC sampler. I can now plot some stuff. And now it's going to come some shock. I think it wants me to click here first. So check it out. The Pasteur distribution for the center of the NB10 population story that we're used to seeing is a distribution that's nice and smooth, centered at a single Pasteur mode. And yet, look, the polyetry is saying that we have actually quite a lot of uncertainty about what that distribution looks like from the point of view of its raggedness. We ignore the part called mu because, remember, it was dummied out. This was a big shock to me when I first started fitting these models, because the reason it's happening is that if you think about trying to learn the center of a distribution and also learn the basic shape of the distribution at the same time, those two things are related to each other, because the shape would have been different if you had taken the data and centered it somewhere else. So not knowing the shape of the distribution increases your uncertainty about the center of the distribution, and that shows up with very unusually ragged-looking distributions that are based upon Pasteur distributions for the centering parameter that have to do with structure in the data about where the data values actually tended to cluster. In this particular data set, if I showed you, what did we call it? We called it sorted, nb10.sorted. Actually, it's waiting for me to go ahead and show you some more pictures, so let me click in here and show you the other one. So not only is the Pasteur distribution for mu, what I would have called mu, the centering, or let's call it theta, the centering parameter, kind of strange. The Pasteur for sigma is also strange. Actually, this is the one for sigma squared. And the predictive error density has heavy tails, just like we would expect based upon what we saw in the data, and a lot of uncertainty about what's going on right in the middle because we only have 100 observations. So if I did a table for you of NB10 that's sorted, you can see that there's a lot of ties in this data set. There happened to be, because everything was rounded to the nearest integer on the scale that they were measuring things on, there are 12 numbers all tied at 401 and 6 tied at 406 and so on. And that's propagating through to these pictures that represent our uncertainty about the actual location of the center of the population distribution. So I believe that's what's going on here. The fact that we have granularity in the data is being translated into these Pasteur shapes. What else can I show you? I can look at the output and see what the Monte Carlo standard error is. I can plot for you those various densities that we're interested in by storing those things and plotting them. And so this is reproduced on in my own code rather than coming from the PT story. The marginal Pasteur for theta is very ragged looking, and the marginal Pasteur for sigma very ragged looking. This is pretty standard for what you're going to get out of Bayesian nonparametric work with fairly small sample sizes. Because location and scale are mixed up with shape, uncertainty about shape is going to give rise to weird shapes of the actual Pasteur distributions for the parameters that you are used to interpreting in the way you usually interpret them. Now, it's my impression that I'm going to need to run this code for quite a bit longer to get values that are as accurate as I would like, because what I've done here is I've summarized the Pasteur mean of the theta parameter, the center, the Pasteur standard deviation, I've worked out the first order autocorrelation, which is still plus 0.75, even though I thinned every 20th. And then I work out that Monte Carlo standard error that I showed you earlier this course, and that number is still a lot bigger than I would like it to be. It's on the order of about 0.08. It's interesting. So I went on to, in the next round of what's here, to rerun the code with a much longer run to try to get the Monte Carlo standard error down to a manageable size. So here I ask it to keep 60,000 observations, thinning every 200, and that multiplies out to 12 million iterations with a thinning factor of 200. That takes about 50 minutes, and I could run that over lunch, for example, and we could look and see how different the results are based upon that. Further down in the file, I make runs with a different piece of code in the DP package that also is able to learn about parameters that have to do with location and scale. There's a function called PT density, and this is basically going to be the analog of what we just saw from Thanasis' code, except where we implement things with a polytree instead of a Dirichlet process. So let's go back here and look around and try to find PT density. That would be up here a little bit. And so, like it says here, this function generates a posterior density sample from for a mixture of polytrees model. And you can look again and see what the model is. And the model is given there in the middle of this page. It says, if you knew what capital G is, the yi's would be IID from G. So that's our usual beginning with exchangeable uncertainty. And then instead of assuming a particular parametric form, G is thought of as we model it with a polytree prior on that underlying CDF. And as usual, there have to be various things that specify where the polytree is centered and how much prior information is stored in it. So his notation, capital pi superscript mu comma sigma squared, says the polytree is going to be centered around a normal distribution with mean mu and variance sigma squared. And then use the same exact convention as before. Alpha represents something that behaves like a prior sample size. And again, you could put a prior on alpha, or you could set it equal to some specific value and see what happens. Yes, please. Yes. I agree. As the mean rather than the median. Right. And that might have created a smoother posterior. I don't know the answer to that question. I think that's an interesting question. I have not been able to explore it myself because the last time I looked at Alejandro's code, the part that involved the mean was broken. So actually, let's see if this PT density thing can do it for us. Let's see. Perhaps the PT density will do the right thing because if we center the prior on capital G at the normal with mean mu and then try to learn mu, the result will be that the mean of the actual Y process will also be mu, and we can learn that parameter. So that's going to come out of here, and we can run the code and see if we get a less weird posterior distribution. So let's have a go. I just mentioned to you that this same code also knows how to do inference where each of the y's, instead of being a number, is a vector. It knows how to do things involving multivariate learning, where the Polya tree prior is centered not at the normal distribution, but at the multivariate normal distribution. But we're not going to do that. And so you can either use a Jeffreys prior or priors that are based upon the usual conjugate sort of thing. And let's see what I did in this code here. So I'm going to, first run, I'm going to show you sets alpha equal to 1 and 6 levels, and it uses this parameter A0 and sets it equal to null, which is going to involve a particular kind of learning. So let's go back here and see what the parameter A0 does. Forget what A0 equals null does. I'm going to run this code anyway and see what kind of answers we get. And then while it's running, I'm going to try to figure out what the meaning of that A0 is. So should run pretty fast. Oh, yes. They are the right. A0 is one of the hyperparameters for the, if you were putting a prior on the alpha, but instead, if you want to have it be fixed at a particular value, you set A0 to null and then set it and then fix it at a value like 1. Alpha acts directly like a prior sample size, and so setting a small value for it is going to try to learn completely from the data. So let's see. All right, so it didn't take that long to run. It looks like it only took a bit less than a minute, in fact, half a minute. And we ought to be able to extract the posterior draws for mu in this and go ahead and plot them just as we did before. So let's see in the earlier code how I did that. I ran code like that. So let's run code like that down here. A little bit too far along. Ah. Okay. Okay, I do have that code. So initially, all it wants to show us is the predictive density. It's getting values that are quite like what it had before. So this is the histogram with the predictive density superimposed on it. It tends to discount the actual outliers without giving them little bumps out there, but it tries to convey the up and down structure of what's happening in the middle of the data set there. But I do want to run this. We should get a sense of what's going on with the parameters now. So actually, I think, Tony, the answer to your question is that when we focus on the mean, we're getting out weird stories as well. So basically, the granularity of this data set with tied values at each integer is being propagated into this posterior distribution. I believe that's what's going on. If we were working with a smoother distribution of empirical distribution of data values, I think we would see something that was smoother here. And so you can see that both parameters are being estimated in a strange, sort of rough manner. We're ready for our next break. So let's take that, and I'll switch topics when we come back after that. So VC Ops, we're going to stop now for 15 minutes and start again at 11:30. The last session probably raised at least as many questions as it answered. Those are disquieting-looking posterior distributions. I don't have answers fully yet. What I'm going to try to do for next time is to create a smoother version of the NB10 data set by adding noise so that all those little lumps at the same exact values are broken up, and we'll see if the result is a smoother version of the posterior. But let's hold that in abeyance for next time. Just to orient you with what's going on in the rest of this file, in which I'm experimenting with PTLM and PT density and DP density, you can now explore inside this file yourself and see what sorts of adventures you come upon. I'm not going to cover all of it in here today, in part because I want to draw the Bayesian nonparametric part of the course to a close fairly soon and go on to a rather more general technique for coping with model uncertainty based on that idea that I described to you briefly last time called calibration cross-validation. But first, one last thing to look at. I gave you a copy of a book chapter that I wrote recently. Let's see if I can find that. Yes, there it is. Back in week 7, there's this great 20th century Bayesian named Adrian Smith, who moved out of Bayesian research and into administration, academic administration, and then administration of research rather generally on behalf of the UK government in recent years. And he had his 65th birthday recently, and there was a conference held for him in his honor, and I gave a talk and then wrote a chapter for this book that they put out. And so I think I do want to recommend reading this as a thing to do to understand what's going on here rather more generally. I will use the NB10 data set as an example. It's a kind of a base note, running base note throughout much of this particular chapter. So we already know how that data set works and we can see what's going on. I'll come back to the unit on calibration cross-validation quite soon. But first I wanted to show you that there is a Bayesian nonparametric unit in here as well. And to show you the results of a little experiment I did, you start seeing the same sort of, I'm now looking at figure 20.5 on page 420 of this particular book chapter. You start seeing very strange spiky sorts of marginal posterior distributions, just like the ones I just showed you, from any of a variety of angles, with polytrees and Dirichlet processes and means and medians everywhere you look. But another thing that I found a bit disquieting was I created a version of the NB10 data that is as close to the normal curve as possible by using the actual quantiles of the standard normal distribution and rescaling them to have the same mean and standard deviation as the NB10 data set. So if you made a QQ plot of this new artificial data set, the points would land perfectly on a straight line because by definition I chose the exact quantiles of the normal distribution. So you cannot build a data set with 100 observations that's more Gaussian than this data set. And I forced it to have the same mean and standard deviation as the NB10 data to try to learn those particular parameters. So now in this table on page 422, I'm exploring the effect of the parameter alpha on the results from the Polya tree modeling. And so I put various priors on alpha. Sometimes I use something like a gamma prior with parameters 1 and 1. That is a distribution that has a mean of 1 and a variance of 1 also. And I contrasted what you get with putting point mass right on 1. I looked at various gammas, 5, 1, 10, 2, 10, 1, and compared with alpha equals 10. And just generally, as you go down in rows in this table, the prior distribution on alpha gets bigger, or the specific value I set it to gets bigger. And the reason I bring it up is that the parametric Gaussian answer for the center of this distribution is right at 404.6, the sample mean of the numbers. And the standard error you'd get from Gaussian modeling is 0.65. What do you notice comparing that 0.65 at the bottom with all these other numbers in this column called SD in the part of the table for theta? Yeah, every single value from the Polya tree in the way of posterior uncertainty about this particular parameter is larger, and in fact substantially larger, when alpha is small. And we only start getting values that correspond to the parametric answers when alpha is really big. So a gamma distribution with a first parameter of 500 and a second parameter of 1 has a mean of 500 and a variance of about 500. And so it's spread out from 0 to square root of 500 is about 20 something. So it's spread out from about 400 to 600, let's say. You're only starting to get values that correspond to the parametric values when you have really, really big values of alpha. And so this is a bit disquieting because the whole idea behind Bayesian nonparametrics was to not put in strong information external to the data set. And the way to do that in the Bayesian nonparametric framework with polytrees is to have a small value of alpha, because alpha acts like a prior sample size. So what we're seeing here is that we only get uncertainty bands that correspond to the right uncertainty bands for this data set if we force the Polya tree to be centered right at the right distribution, but with a huge amount of prior information centering it there. If I make alpha go to infinity, you can see from this table that the Polya tree results will, in the limit, match exactly the Gaussian answers. But alpha going to infinity corresponds to pretending that the data are normal and ignoring what the data has to say, pretending that the data are exactly coming from the centering distribution and ignoring what the data has to say. So I found this quite disquieting. Essentially, what this is saying is that when you try to be nonparametric and really say you don't know what the underlying distribution is, you pay quite a high price. Your intervals become substantially larger, substantially wider than they would have been. Now, this comparison is not quite fair because I'm comparing what the Bayesian nonparametric answer gives with an answer that I stacked the deck and knew what the right answer was. And in general, if I was working with data sets that I wasn't the one who created, I wouldn't know what the right answer is. You could think of the wider intervals coming from the Bayesian nonparametric story as representing a kind of insurance policy. It's the price you pay for not really knowing what the data generating CDF is. But what this table shows is that that price can be quite large. And if we compared the BNP answer with an answer based upon not quite knowing exactly what the data generating story was, but being able to learn it by another non-Bayesian nonparametric means, I think we might still find that the Bayesian nonparametric story is rather more conservative than we might have expected it to be. So, well worth reading a bit more in depth in this chapter. I'll come back to it because I want to do the calibration cross-validation stuff. But that's about the last I'm going to say about Bayesian nonparametrics in this course, with the exception perhaps of circling back around and trying to do a few more experiments between now and next Friday to show you if we can understand why those posterior distributions were so strange and spiky. In principle, the Bayesian nonparametric story, why have we been doing this for a number of hours last time and this time? Well, you recall it was one of the three basic ways that we developed to try to cope with the fact that we're not actually sure what the basic sampling distribution should be. I'll go back to part 5, which is where we want to mostly be now. I'll go ahead and get rid of that. And I will also go back and grab that chapter that I just wanted to talk about. Store that on the desktop as well, because we'll be coming back to that in a minute. So returning to the main line of the lecture notes about Bayesian model specification, we have these 4 ingredients that we're trying to specify. I'm on page 22 now, what we usually call the prior, the sampling distribution, the action space, and the utility function. And our job is to figure out how to start with the problem we're working on and create a good mapping from the problem to those 4 ingredients. And this is quite a dilemma for all theories of statistics. The frequentist problem has exactly the same, the approach has exactly the same difficulties, except they don't acknowledge the need to specify a prior. And I mentioned on page 32 that there appear to be 3 ways forward to try to do a better job of assessing and propagating your uncertainty in the model than simply pretending that you have no uncertainty about the model. One of them was Bayesian model averaging, which we've looked at in some length now. One of them, Bayesian nonparametrics, which I'm going to draw to a close now, and then we'll talk about calibration cross-validation and begin looking at some examples of it. So before we close the book on Bayesian nonparametrics, I'll ask you to reflect for a minute and see what we learned. It's a technique that holds great promise for being fully adaptive. According to the way things are set up, you're allowed to relax standard parametric assumptions that you always, as a statistician, were worried might not be true. Gaussian error assumptions, Gaussian assumptions on error distributions, particular assumptions for the way sampling distributions in other contexts behave. You would like to be able to relax those assumptions and learn what the truth is from the data. Bayesian nonparametrics holds the promise to do that, but you can see from what I've shown you here that, first of all, the answers you get may turn out to be more sensitive to those hyperpriors that you have to set than you might like, and you need to gain substantial experience in actually setting those hyperparameter values. I said before, for example, in Thanasis' code that the program was like a box with 8 dials on the outside. There's those 8 hyperparameters you have to set, and you get different answers based on what you set. Living in England for 8 years, I learned a valuable English word, a British word that is part of their version of English rather than ours, and I forget if I've used this word so far in this course. A British person would talk about a particular task as being fiddly, F-I-D-D-L-Y, and what they mean by that is filled with small details, all of which have to be done exactly correctly. And that's quite a useful word, right? Because that takes me about 10 or 15 words in American to say, and every Brit person knows that when you talk about something being fiddly, that's exactly what that means, that whole phrase. For me, as a user of Bayesian nonparametrics with quite a bit more experience in it than you guys, even for me, the process of specifying the prior through either the polyetry or the Dirichlet process is rather more fiddly than I would like. And so if someone who was a world expert in Bayesian nonparametrics had been teaching this class for you, probably it would have looked a little bit less fiddly because this person would have had a lot more experience with it than I have so far. I still think of Bayesian nonparametrics as an important technique in general for learning things from the data without pretending that you knew them already. This does hold that promise, but you can see that the actual details have the character of being a little bit fiddly, and all of us in the room need more experience with this process. Also, the MCMC that's necessary to fit these models does not necessarily scale very well with really large sample sizes, really large amounts of data. And so that will be the principal topic I'll be covering next time as our last central topic about how to do approximate Bayesian calculations with large data sets. So returning now to, yes, please. Uh-huh. That's true. Um, so for posterity, what Tony was saying was that a standard frequentist thing to do to check model assumptions is residual analysis, and there will certainly, of course, be Bayesian analogs of that. Another analog of that process that that unfolds rather more naturally in the Bayesian story than the frequentist one is model checking based upon predictive distributions, because that's another way to look at the quality of the assumptions. If you make predictive distributions for each observation, and if you want to do it in a full jackknifey sort of way for cross-validation, you leave out the observation that you're trying to predict and bring in the rest of the data and do that for the second observation also, y2 given y minus 2 in the background, and so on. These predictive distributions, according to if you're in a regression setting, for example, where there's an x for this particular observation as well, these predictive distributions don't have to look the same for each observation. Some of them could be quite strange looking in relation to other ones. Some of them could be quite flat and so on. This is some analog of residual analysis because each observation has a residual attached to it in regression modeling. And each observation also has a predictive distribution attached to it from the Bayesian point of view. And so we can look and see how the observation matches up with its predictive distribution. And if we start finding lots of observations that are extremely far out in the tails in their predictive distributions, that would be a Bayesian way to talk about the fact that the residuals from the model are much bigger than we would like them to be. So I think you're right that there is a direct Bayesian narrative that's based upon residual analysis, but there's also a direct Bayesian narrative that's based upon predictive distributions, and in some sense they parallel each other. So a reminder of what calibration cross-validation does from last time, and then we'll start looking at an actual example of it. We partition our data set into 3 subsets rather than 2. I'll call them modeling, validation, and calibration. Then we use the modeling subset to explore lots of models. Let's say to simplify things, you found one particular model that looks really good. Then you build predictive distributions from that model for the data in the V part, the validation part, and see if you validated well. And I'll say more today about this log score idea that I mentioned last time as well as a measure of the predictive accuracy. You will often find that the models don't validate so well. And so you go back now to step B and remodel and revalidate and keep doing that until you find a model that does validate well in V and also seems to validate well inside M. At that point, you merge the M and V parts of the data together into one larger data set, and you fit the model that you found by this iterative process to all the data in M union together with V. And then you can create a report for people that has 2 parts to it. One is the inferential and predictive summaries that you get from the data in M union V from your best model that was found iteratively. And the other one is you have data left over in the calibration part to talk about the predictive accuracy of that model on data that was not used in the fitting process. So we actually get out a kind of 2-dimensional summary, not only a good answer to the main question that has paid a reasonable price for model uncertainty, but also an indication of how well calibrated the iterative process that led to that particular model, how well calibrated that process is on something that is a good proxy for future data. And as I mentioned, machine learning people have been partitioning their data into 3 subsets for a while now as well. Train, validation, test is a phrase that you see in the machine learning literature. I have tried to improve a bit on the machine learning version of this by 2 ways. I know how to write down utility functions that help me decide how much data to put in each of those subsets. And also, I believe that this process is valuable potentially not only for large data sets where it gets emphasized a lot in machine learning, but also in in small and medium-sized data sets as well. And I think we talked last time, I believe we did, am I right? We talked about this algorithm for model search. You are now free to run an algorithm like this in the context of calibration cross-validation. You can fire this algorithm up on the modeling data set and use it as a way of exploring alternative models until you have one that seems to be good, and then see how well that model validates on the validation part. And there will be a certain amount of going through the first 4 steps, going down to the 5th one, going back to the 2nd step, and iterating B, C, D, E, B, C, D, E, until finally you stop at B. And we have implementation issues to solve, which we're going to solve today, namely, how do we decide when one model is better than another from a Bayesian perspective, and then how do we decide when to stop? Let me postpone those until after lunch and show you a case study in which I do the CCV approach. So let me come back to this chapter that we started to look at before, and let's look now at trying to use calibration cross-validation with the NB10 data. So there's the same algorithm you saw a minute ago written out a little differently. And so now here's what I did. I randomly partitioned the 100 NB10 data values into M, V, and C subsets of size 50, 25, 25. Those seem to be reasonable general purpose fractions to put into each of the 3 subsets. And the result is this data set you see right here. The raw data set is at the top of table 20.1, expressed as a frequency distribution. And then it turned out on my particular random partition, I got the modeling data you see under that script M sort of symbol, and the validation data and the calibration data. With the data set this small, it would be ideal, instead of doing this partitioning once, it would be ideal to do this partitioning multiple times and average over the results. But in fact, here I'm going to show only results with the partition right there. So now we've done part A. We've partitioned the data randomly into those 3 subsets. So step B now says, let's start modeling on the part that's the M part of the data. So given the problem context, it would be natural to begin by fitting the parametric Gaussian model that pretends that the data come from a normal distribution, and then you put a prior on the parameters of the normal. And like it says at the bottom of this page, at the point at which these 100 weighings of NB10 were performed at the National Bureau of Standards back in the 1960s, it's likely that people who were working there already knew quite a bit about the weight of this block of metal, and also they probably knew quite a bit about the accuracy of their weighing process. But here I'm going to illustrate the analysis from the viewpoint of someone like me, and probably you, who has little information external to the current data set about that actual weight. So I want to use diffuse priors. And so I'll use a prior that in which the joint prior is the product of the marginals, and I use the usual sort of prior for theta, the true weight of NB10 that's a normal with mean 0 and a really big variance. And I use an inverse gamma prior on sigma squared with really small parameter values. That's that gamma epsilon epsilon prior we've talked about before. So with this prior of the Gaussian model, it fit only to the data, the modeling part. You can run WinBugs without much trouble, and you find the following summary. So the marginal posterior for theta is approximately Gaussian, centered at 403.8, which turns out to be the mean of the 50 numbers in this table right here, and standard deviation given by 1.00. Therefore, a 95% central posterior interval for theta runs from about 402 to 406. The marginal posterior for sigma looks a bit skewed, as you'd expect for a scale parameter with a mean of about 7 and a standard deviation of about 0.7. And the posterior predictive distribution for a future observation is also approximately Gaussian, with the same mean as before, and of course with a standard deviation that looks a lot like the posterior mean of the sigma variable, around 7.2. Therefore, the 95% central posterior predictive interval for the next data point runs from about 390 or so up to about 418. So at this point, I could either do something that is internal to the modeling data set that measures how well this model fits, like calculating the BIC value for it, as I'll show you after lunch, or calculating the DIC value for it, or calculating the log score value for it, although all three of those quantities don't have any direct absolute interpretation, and instead are interpreted relative to some other model. So you have a particular figure of merit sort of number for one model, and then you do the same figure of merit on another model and try to find the one that's better according to that figure of merit. But another thing we could do is just say, well, suppose we temporarily tried to stop with this model here and look and see how well it validates. So in fact, I'm perfectly free. I haven't left the part where I'm modeling yet. I'm perfectly free to see how well that model validates on the very same data set that I fit it to. So here I have created in this figure, a calibration plot. I compare nominal and actual coverage of 100 times 1 minus gamma percent predictive intervals as gamma runs from 0.01 up to 0.99. So we would be used ordinarily to creating a 95% predictive interval, but I could certainly create a 98% one and a 99% one and a 14% one and so on. And so I'll show you, the left-hand panel shows what happens when you use this model to see how well it's calibrated. And there's the calibration plot from the Gaussian model, where the data set, where the data has been used to fit the model, and the very same data set has been used to validate it. So let's look at this picture and see what it means. The solid line is meant to be the 45-degree line, y equals x in this picture, and it's the target behavior if we're well calibrated. What does it mean that the dotted line, which is the actual calibration curve for this model, lies essentially almost entirely above that line? Does it mean that the Gaussian intervals are wider than they need to be, or narrower than they need to be, or about right? Well, let's see. Pick a value like 60% nominal level. If the Gaussian model were well calibrated, the 60% nominal level would be associated with a 60% actual level. But instead, the actual level at nominal level 60% seems to just follow it on the way up. It seems to be around 90%. And so actually what this is trying to say is that the Gaussian intervals are too what? Too wide or too narrow? No. When we ask for 60% coverage, they're actually covering 90% of the time. They're too wide. They're substantially too wide. Isn't that interesting? Now, why could that be? Because what? Because the variance is inflated by any outliers that are present, and the normal curve is not expecting outliers, and so that creates a much bigger variance than the normal curve was expecting. Yes, that's a good way to say it. The right panel here is a normal QQ plot of the 50 observations in the M part of the data, and you can see we do have two outliers, a big one in each tail, and so the standard deviation is a lot bigger than it ought to be as far as the normal curve is concerned, and that makes the intervals from the normal model much wider than they need to be. Another way to talk about it is to remember that remark that I made some weeks ago. Among all symmetric distributions that live on the whole real line, the Gaussian or normal distribution actually minimizes Fisher information for location. In other words, it actually is creating wider intervals, because minimal Fisher information means maximal standard error, right? So it's actually creating wider intervals than necessary, except on those occasions when the actual data generating mechanism is Gaussian, in which case it delivers the right intervals. They are correctly wide. But for other data generating families, either heavier tailed or lighter tailed than the normal tends to produce conservative intervals. You ask it for 60% coverage when the normal model doesn't fit well, and it gives you back 90% coverage. That's what the picture on the left is saying here. You can see, like it says here in the paragraph above equation 20.5, you can see that the Gaussian model produces predictive intervals that are sharply conservative. For example, at all nominal levels from 70% to 95%, the actual coverage is 96%. And the right panel gives a normal QQ plot of the data, and that identifies the reason for the poor validation of the Gaussian model. The distribution is unimodal, that's good, and is close to symmetric, that's good, but has substantially heavier tails than the Gaussian, and this has led in the Gaussian framework to a larger estimate of sigma than is somehow appropriate. And so that's probably a good way to begin carrying out step B in the calibration cross-validation algorithm. Use M to explore models until you found one that seems good. And even before seeing how well it validates in V, you can see how well it validates in M. In fact, that can create a kind of bounding argument, because if it validates really well in M, you could say to yourself, well, the reason it validates well is I use the same data to model and to validate. But this is the opposite of that bounding argument. I use the same data to model and validate, and the model does terribly in this picture here on the left. So, wow, this is a bad model. So that suggests model 2, as we talked about fitting earlier this quarter, or rather earlier this course, namely that instead of the data being IID Gaussian, their IID draws from a T distribution with unknown degrees of freedom. And so we fit this model before. I showed you those results quite a bit earlier. Easy to fit via MCMC. 100,000 monitoring iterations only takes about 15 seconds at decent gigahertz. And that's a big enough sample size to get Monte Carlo standard errors that are really tiny, less than 0.01. And I used the same diffuse prior as before, except I put a uniform prior. In this case, I ran from 1 to 10, broke my rule for some reason about having the prior not go below 2 degrees of freedom into the region of infinite variance, but you get the same thing either way. All right, so that's the T model. Let's see what it does. And it produces quite different answers. The marginal posterior is again approximately Gaussian. This time the mean is 403.4 and the standard deviation is only a half, whereas before the mean was 403.8, which is close, but a standard deviation of 1. So the T distribution has an internal estimate of uncertainty that's exactly half what it was from the Gaussian. That's got to be in the right direction, right? Because we saw the Gaussian was producing uncertainty bands that were too wide. So now we're getting a band that's driven by 0.5 as its standard deviation, not 1.0. The 95% central posterior interval is much narrower. The marginal posterior for sigma, again, has moderate positive skew. But now look, the values for sigma now look more like around 3 rather than around 7. And the marginal posterior for nu is centered at around 2.5 or so degrees of freedom and a pretty big posterior standard deviation. And the posterior predictive distribution for a future observation is again approximately Gaussian, but much narrower than before. It now has a posterior standard deviation that's a little bit bigger than the one we get from the mean, or rather the center of the distribution for sigma. And the central posterior interval for the next data point runs from about 398 to 409. It used to run from 389 to 418. So these predictive distributions are way narrower than the Gaussian ones. And that's got to be right, because the problem with the left-hand panel in figure 20.1 is that the Gaussian was producing intervals that were far wider than necessary. So, note, it says here, how much smaller both the inferential uncertainty about theta and the predictive uncertainty about future observations are with the T model than with the Gaussian sampling distribution. This is a consequence, as I mentioned a moment ago, of the Gaussian having minimal Fisher information for location. The much smaller values for sigma are because observations from a T distribution have variance nu over nu minus 2 times sigma squared, and that means that scale and shape are confounded, so I can't really talk about sigma as having the same meaning in both models. Now, is the T model better than the Gaussian? Well, one way to answer that would be to do that validation exercise again. And let's see if I did that. There should be a picture down here maybe where I did the validation exercise again. Yes. And so the left-hand panel of figure 20.3 offers a calibration plot for the T model in which I fit to the data in M, and then I went ahead and validated in M. And you can see the new calibration curve is in the left-hand panel here. It looks real different from what it did before. The previous curve was showing very violent conservative behavior. Now, would you say this model is calibrating well internal to the data set on which it was fit? We would like the dotted curve to match the straight line pretty closely. And it does sort of look like the straight line, but to the extent that it's not on the straight line, it tends to hang around where? Above it or below it? Below it, meaning that when you ask for, let's say, 60% coverage, you actually get only about 40% coverage. So that's a consequence of overfitting when you try to validate on the same data set. I mean, it's a, or no, it isn't, is it? Because we would have expected, if you use the same data to both model and validate, you would have expected this picture to show an optimism with respect to calibration. So actually, this is trying to show that on this particular data set, maybe the T model, even the T model doesn't fit all that well because it's producing intervals that claim to cover 60% of the time, let's say, and are only covering about 40% of the time. So that's interesting. Then when I fit the T model to the data in M and try to validate in V, the performance is even worse. Alleged 60% intervals are only covering about 20% of the time. And part of that is resulting from the instability of only having 100 data points. Because the validation data set now only has 25 observations in it. That's partly why there aren't that many, partly why it has so many flat spots in it, this calibration curve. And the other thing that's going on is that the original data set, did I do a normal QQ plot for you of the entire data set? Not in this chapter here, but I've shown it to you before. The entire data set achieves its T-ness, so to speak, on the strength of precisely three major outliers. Two of them happen to fall into the modeling partition this time. And I don't remember whether the other one fell into the validation or calibration partition, but basically these pictures are rather unstable as a function of which particular data points happen to fall into the partition sets, right? So that's why if I were doing this carefully, I should really do it over and over again for a lot of random partitions and average these curves. That would give you a more stable sense of what's going on. But another way to see whether the T model is any good is to calculate the log score for it. So, and as I mentioned before, the idea with a univariate data set like we have here that just has a bunch of Y values, and let's say we have two models, M1 and M2 we're going to compare, involves computing the following two things. I'll do this first for model J as J equals 1, and then I'll do it again for model J when J is 2. So equation 26 says the full sample log score, LSFS, for model J, given the data set and the background information, script B. To calculate it, what you do is you take the logarithm of the height of the predictive density for observation yi at the point that actually occurred, y sub I. Given the whole data set, that's why it's called the full sample log score. It uses the full sample in order to predict each observation, and given model J and given the background information, and you average those guys across the whole data set. This might seem like it uses the data twice, and it does in a gentle way, because I'm using observation yi to the right of the conditioning bar and then asking how good the predictive distribution is for that same observation to the left of the conditioning bar. But in fact, you can show without much trouble that even for moderate sample sizes, less than 100, the effect of that is not large. And certainly with 100 observations, the predictive distribution with any given point taken out doesn't actually change that much, even with the outliers, when we're talking about the outliers. So that is actually my favorite quantitative measure for comparing models. And now the next question is, how do you compute it? And the answer is, you were fitting the model with MCMC anyway, and so you can use the MCMC output to compute the log score as well. So if you think about what that predictive distribution is that we're about to try to evaluate, pardon me, on the right-hand side of the equal sign in equation 20.6, then we can write it as the top equation in 20.7 with little m identically distributed, of course not necessarily independent MCMC monitoring draws from the Pasteur distribution. This is a general parametric model with parameter vector eta in eta j in model mj. Then you go ahead and make a bunch of MCMC draws of that vector. And so the first equation in the set of equations that's called 20.7 is our familiar equation for constructing a predictive distribution. You take a weighted average of the sampling distribution for the new observation weighted by the Pasteur distribution for the parameters. That's always been our equation for making predictions. But look, when you have something times a density, that means that you're working out and integrate over that. You're working out the expected value of the something. And so that's actually the expected value of the height of the sampling ordinate at y star, given the parameter vector eta j, and then we compute the expected value of that over eta j. But look, we could either compute that integral exactly, or we could approximate it with Monte Carlo means. If you want to work out a Monte Carlo approximation to an expected value, then just go ahead and take a lot of draws of that parameter eta j from its distribution and average the resulting expression evaluated at those draws. That's a basic idea for Monte Carlo as a way of approximating integrals, in particular approximating expectations. So actually, it's not very hard. After I've written down all those monitoring draws, it's not very hard. I have a closed form density expression for the actual sampling distribution of the next observation. In this case, it's the density curve for the T family. And I just evaluate that density curve at each particular row of the MCMC data set. And that will give me the predictive ordinate that I need for the log score. So let me now show you what I mean by that. I'm going to grab this guy here and kill him off for a moment, because somehow every time we go into the PDF world for a little while, when the resolution of my machine has to be mapped onto the resolution of that camera, wherever it is, sometimes I lose control of the screen. So I have some stuff that I've put onto the data set down here under the data sets that will help us to work this out. Down under the NB10 case study, I have carefully saved for us the draws from the Pasteur under each of several different models. So let's look at model 3. Model 3 fits what sampling distribution to the data? Gaussian. That was what I called model 1 in my CCV search here. So model 3 is the wrong model. It's a bad model. It's a Gaussian model with flat priors for mu and sigma and a predictive distribution. That's good. And under model 3, I ran the MCMC already and saved a whole bunch of the monitoring draws. Looks like I saved 100,000 of them. Also under model 3, I saved the monitoring draws for sigma. And I find it strange that I saved the monitoring draws for nu when there isn't any nu in model 3. So something seems to be mislabeled here. This is called model 3, but I believe is actually really model 4. I don't know what Model 3 is. It's probably got a little bit of a different prior than Model. Let's look at it. Model 3, yeah, it's uniform 0 to 9. This one here has, well, you see any difference between those two models? I don't. So it looks like I messed up on defining the web page here. Model 1 is the T model. And for some reason, I've called the output of Model 1 NB10 Model 3, mu and sigma and nu. So if you accept my apology for having mislabeled these files, mu and sigma and nu are actually the names for the draws from the posterior from Model 1. And Model 4-mu.txt is actually the name for the draws for mu and sigma, this one down here, from the Gaussian model. So now I can finally run some R code to do this. And so the R code is going to want to have those things in a particular place and then go ahead and read them. So let's download each of them and store them there. So I'm going to need this file here, which I will save to the desktop. And this file here, which I will save to the desktop. And this file here, to which I will do the same thing. And this one. And finally this one. When I'm done, oh good, there they are. And I can now create a new directory. I've got one already called NB10 log scores. Oh look, I did that already. I'm sorry, I wasted your time. What's this one here? Yeah, that's the right one. Good, so I have everything already set up for us. We didn't need to go through that little exercise, so now I'm going to run the code. I'll explain the code to you and run it. So here we are in R. I'm going to change directory to that place we just found actually secretly already had the right files in it. Now I'm going to download that this thing. I'm going to bring it over there and run it. I guess I can go ahead and just toss all these other guys into the recycle bin. I needlessly downloaded them. But now let's look at this code for a minute. First, it grabs the data using the dget command. And I think having set the right thing, it should be able to find that. So let's look at Y. There's Y. Then it's going to pull in all these guys here. And I see now why I called them Model 3 and Model 4, because they were already in this file called Model 3 and Model 4, but that's not a good reason to confuse us about those names. And so each one has 200,000 observations in it. There is no built-in function in R for the density of the scaled t-distribution. So I've written one here for us. And now I just do the following. I create a matrix filled with zeros that has 100 rows and 2 columns, 100 being the number of data points. And in the first column of this matrix, I work out the contribution to the log score from the T model. And in the second column, I work out the contribution to the log score from the normal model. And you can see all I'm doing is I'm just using that particular, I'm using those values from the MCMC to define these log mean calculations. Let's go ahead and fire it up and run. And it takes a little minute to run, but not too bad. And now let's have a look at how things went. So for each of the 100 data points, sorted from smallest to largest, I have the contribution to the log score from the T model and the contribution to the log score from the Gaussian model. And if you look back at the way log scores were defined, somehow I lost that a while ago. I guess, yeah, I had to shut that down, didn't I? You look at how log scores are defined, do we want them to be big or small if the model's doing a good job? Yeah, we'd like them to be big because if the model's any good, the predictive distribution, the height of the predictive distribution at the observed point will be large, because that will mean that the center of the distribution is close to the actual value itself, and therefore the height will be large. So we want large log scores, and look at what we got. At the outlier in the left tail, the T model is much better than the Gaussian model. Also, at the next two observations, the T model is better. Then there's a long string of data points where the Gaussian is actually slightly better than the T model. All those zeros there stand for Gaussian being better. In the middle of the distribution, and then all of a sudden funny, I thought the T model was better. Some of the values in the very middle as well. That is a little strange. And then out in the tails again, the T model is better. That does not fit what I remembered. Let's work out how often the T log score contributions are bigger. Yeah, I think there's something wrong here that I might have to fix during lunch. This all seems like it's not producing what I was expecting. It does turn out that the log score for the T model is bigger than the one for the Gaussian model, because minus 3.23 is in fact bigger than minus 3.26. But as people who have no experience prior to this in consuming log scores, you have the right to say, boy, that doesn't seem that much bigger. How do you know when a difference in log scores is big enough to matter? And that's a question I'll try to answer after lunch. But basically, the T model really does fit a lot better than the Gaussian does, and yet the log scores aren't that different from each other. So what this picture shows is that the T model, and this is a little different. That's just strange. I don't know what went differently here. I'm going to have to sort that out at lunch. When you look back at the corresponding picture, yeah, this is the right picture, and I don't know what went wrong with that code. What you see is that the T model is better at the extremes in the data, which makes very good sense. Then there's a region in the middle where every now and then the Gaussian model is better than the T model, because these are individual log score contributions on the vertical scale as you go from the data values sorted from smallest to largest on the horizontal scale. In this region right here, the Gaussian is a little better, and in this region right over here, the Gaussian is a little better, but the T is better in the middle, and it's better at the edges. And so there's a small region in which the Gaussian is better. And that did not come out when I ran the code this time, which is quite strange. So I'm going to have to sort that out at lunch. I don't know what went wrong. But the picture's basically showing that the t-model fits the data a lot better than the Gaussian because almost everywhere you look in the data set, the log score for the t-model is higher than the log score for the Gaussian. So I'm not sure why that happened. But let's have a look at what the rest of the story is along here. So, oh, I'm getting quite different answers too. Applying this method to models, the Gaussian model and the t-model yields log score values of minus 3.3 for the Gaussian model and minus 2.86 for the t-model, which are very much farther apart than those values I was showing you a minute ago. So there's something wrong with those MCMC draws. I'll probably have to run the MCMC again over lunch to make sure that we get the right answer. And given that we have experience, that I have some experience with log scores, this actually represents a sharp preference for the t-model. And I've shown you already this figure that shows the t doing better. In fact, it turns out that 80% of the data values in the modeling part of the data set are predicted better by the t-model than by the Gaussian. So looking back at the steps of calibration cross-validation, we have now created an ensemble that has two models in it. M1 is the Gaussian, M2 is the t. And I have now discovered that model 2 is better than model 1. And I could perhaps also remind you of where we were in here, where we're following along on that algorithm for looking around for good models, which should be coming up pretty soon, right there. So we started at the Gaussian model, which here is called M0, but for some reason in the paper I called it M1. And I set the current model ensemble to just that model and the current model to M0, the Gaussian. If M current is good enough to stop, and we saw that it wasn't because we found that it calibrated very badly on the data in the various data set that it fit with, then we went to C. We generated a new candidate model by looking to see that the T model fits the data better, and so let's go with that one. Then we found that M new is better than M current being previously the Gaussian, M new being the new one. And so we set M current to M new, and I'll go back to B. So now basically we are asking the question, is the T model good enough to stop? And that requires thinking about how you would make that an answer to that question operational. How would you decide when it's a particular model is good enough to stop? So now I'm back here. I see. That's what happens. Now I'm back here. And what I said in the chapter was, is the T model better? We just worked out the answer is yes. Is it good enough to stop? The answer is complicated here by the small sample sizes in each of the two partition components, M and V. And here I've shown you in this figure, we have calibration plots for 3 different data configurations, and in all cases, the T model is being used to calibrate. So in the left-hand one, I fit to the data in M and validate in M. Fairly good, but actually the intervals look like they are a little narrower than they should be. Then I fit to the data in M and validate it in V, and the calibration is terrible. The intervals are all much too narrow. And then I just tried to see what would happen. I fit to validation data set and validated on the validation data set, and the calibration is perfect, absolutely perfect. So internal validation, which is where you use the same data set to both model and validate, that would be the left-hand panel and the right-hand panel. Internal validation ranges from barely adequate in the left panel to excellent in the right display, but external validation, evaluating the fit on new data not used in the fitting process, is abysmal. And it's it has the opposite calibration problem, namely predictive intervals that are not wide enough, the opposite problem to what we saw before. But with only 50 observations in the M and V and 25 in the V subset, the problem is basically that the parameter estimates from the T model are quite unstable as a function of which data points happen to land in the partition sets. So I made a little table that shows what's going on. There are 4 rows to the table according to which data partition the model is fit to. Here in all the entries in this table, I'm fitting the T model to various subsets of the data. And we have sample sizes ranging from 50 down to 25, up to 75, up to the whole data set 100. And in each case, I show you the posterior mean and standard deviation of each of the 3 parameters in the model and the predictive distribution. Well, look at the theta column, and look how different the answers are according to which data set you use for fitting. The basic problem here is that there are only 3 outliers in the whole data set. 2 of them happen to fall into the M subset, and 1 of them, it turned out, fell into the C subset. And so when you fit the T model just to the V part by itself, you get a really bad sense of what's going on because there aren't any outliers. And all the way across the table, you see that the row called V alone produces answers that are really different from the other answers, and that's because that happened to have been a little partition that didn't have any outliers. So we're having a little trouble deciding whether the T model is good enough to stop because we have this instability that's based upon how many of the outliers happen to fall into the different partitions. And we'll try to see where this goes after lunch. Looks like it's time for lunch. So VC Ops will break for an hour now and start again at 1:30. Thanks very much.